midterm. So I'm thinking of a week from this Wednesday, okay? So it'll be next Wednesday. And we're going to have, this is almost a 2-hour class. We're just going to take the second half of the class to do the midterm. It won't take up the entire class period. So it will be fairly simple questions, basically testing, sometimes even asking for definitions of things. It will be a closed book. Because of this, it will be a closed book exam. And be fairly, I should say, very simple questions, testing you whether you have understood some of the basic concepts and maybe do very simple calculations at most, okay? So this will be a sort of a 1-hour test to be held in the second half of the class period. And it will be on next Wednesday, a week from this Wednesday. And it will cover everything we have done until the end of the present chapter, which is chapter 6, right, in the notes that I have given you. So everything that we have done so far up until the end of chapter 6, the one on basic group theory, okay? All right, so let me just write it down in here. Midterm 1. In class. Next Wednesday, 1-hour test. Okay.
So you said no. Not
Closed book.
notes.
No, closed book notes. Yeah, close everything. Because it'll be very simple questions. Okay. Okay. So we talk about this important theorem in group representation theory called the homomorphism theorem. Basically, it's forming the quotient group of some group divided by its one of its normal subgroups, and then finding the kernel, and then I'm sorry, the group that we are thinking of is the quotient of the group itself with a kernel of a homomorphism, and then the theorem says that that quotient group is isomorphic to the image of the homomorphism mapping. And so now, before we go on to the next thing, let me just introduce a couple of concepts to you, although we won't be making direct use of that. These two terms appear very often in the application of group theory and to physics, and these are the concepts of simple groups and semi-simple groups. And these are defined in terms of so-called normal subgroups of a given group. So if a particular group does not have any normal subgroup other than itself, then it's called a simple group, okay? So you see, let's say that this is some group, and now sometimes we can find an invariant or normal. The two terms mean the same thing, okay? In invariant subgroup, H satisfies this condition that GH is equal to HG for any G in the group. In other words, H is invariant in the sense that H is equal to G minus 1 HG, okay? So you imagine taking sort of for any G, taking and this applies to any group element inside of H. Now the two elements in here need not be the same, okay? So if the similarity transform of some element inside of H leaves you with something that's also in H, then the subgroup H is called an invariant subgroup. It's invariant in this sense. H goes to H again, okay? Now, sometimes we have the case that H is a proper invariant subgroup. Proper meaning that H is smaller than G. okay? But sometimes there may not be such proper groups. But of course, G itself can be considered as an invariant subgroup. Any set is a subset of itself, okay? So the whole thing, G may be considered, G is always, in fact, an invariant subgroup of G itself. So if you have the situation that some group G does not have any invariant subgroup other than itself, then it's called a simple group, simple in that sense. It does not contain any proper invariant subgroup, okay? Then it's called simple. And some groups in physics are very, some groups such as SU2, SUN, the unitary groups, special unitary groups. The most important one of which is this one, which is the one which covers the rotation group. We'll talk about this later on. Special unitary groups are simple, okay? Now, what is semi-simple? A semi-simple is something that's not quite simple, but only semi-simple, in the sense that it does not contain any a billion invariant subgroups, okay? It may contain some subgroups, invariant subgroups that are non-abelian, but if it does not contain any billion invariant subgroups, then it's called semi-simple. I won't copy down what I have just said. This is definition 6.4 in the notes, so you can look at it. Semi-simple groups are also very important. The special orthogonal groups that we have looked at are all semi-simple, such as SO3, SO4. And also, later on, we're going to look at one particular group that's of the utmost importance in physics. That's called a Lorentz group, and that's semi-simple also. So I'm just giving you some examples. All of these groups that I've written down are of tremendous importance in physics. And so the theories of the representations are consequently very important also. Yeah?
Is SU2 semi-simple?
SU2 semi-simple. Oh, no, simple. Simple group, yeah. No. SU2, but not, well, if it's simple, then it's semi-simple. It's totally simple, okay? Semi-simple is only so simple, but not altogether simple, okay? All right, so I just want to mention these couple of terminologies, the details, examples, and so on, application to specific groups, and so on and so forth, we'll consider somewhat later if we have the time. So now, for the time being, let me go on to the next very important concept in group theory, which will prove to be very important in a particular application to quantum mechanics and classical mechanics as applied to the group SO3, the so-called Euler's theorem, which pertains to how you describe any general three-dimensional rotation. And some of you have taken classical mechanics will have heard of the notion of the so-called Euler angles, how you describe rotations in Euler angles and so on and so forth in classical mechanics. And so we will find out that using this theory that I'm going to develop, in fact, we can prove the so-called Euler's theorem, which states that you can describe any rotation at all in three-dimensional space by means of three angles. One particular choice is the so-called Euler angles, and we'll lead up to it, okay? But in order to build up to this final theorem, we have to introduce the notion of a group action first. Group action. Well, technically, mathematically, the group action is a map. We call that map sigma. It maps from the product set, the group multiplied by some manifold, going to something in the manifold. So this is very abstract, okay? So what it says is that if you take a particular group element G, which is inside of the group G, and you take some X inside of this, usually a differentiable manifold, okay? Then the group action will map using G, will map the point X to something else in X, okay? Which we are usually going to write as G acting on X, okay? It's very abstract like this. Now let me immediately give you the most obvious application of this, okay? Let's take the group SO3. Now technically, SO3 is just the set of 3 by 3 special orthogonal matrices, right? It's an algebraic concept, right? Nothing about geometry at all. Anything in SO3 is a 3 by 3 special orthogonal matrix, okay? Now we call this SO3, well, because of that property, but you know that we have come across this many, many times already, both in this course and elsewhere in classical mechanics, that SO3 is a set of three-dimensional rotations, right? And what is an object, what is a three-dimensional rotation good for? It's good for rotating something in three-dimensional space. That's what it does for a living, okay? And so you can think of, for example, some matrix, 3 by 3 matrix in SO3 acting on some point in this differentiable manifold, which we can identify to be, for example, three-dimensional Euclidean space, okay? You can think of, for example, the entire three-dimensional Euclidean space as being a vector space in this sense. So you choose a point which you call the zero of the vector space, and then you set up some coordinate system in this space. And at any point in this space is then the same, any point in this space, let's say this one, is then representable as a three-dimensional vector, okay? And this vector is given in terms of its 3 components, x1, x2, x3, with respect to this choice of basis states. And so your SO3 matrix, which is a special orthogonal matrix, can then be thought of as some operator that acts on this 3 vector to give you what? To give you another vector which is also of the same length as the original vector, okay? And which has and which can be thought of as being a vector that is rotated from the original vector. So x prime 1, x prime 2, x prime 3. And so if you think of some rotation, this one being rotated to here, then this is x prime. Okay, there's some rotation. Let's say there's not a particular one, but there's some rotation which rotates you from this vector to this vector like that. Okay? So the idea is this group can be thought of as a set of machines, if you will, okay, each of which would do some rotation to something in this three-dimensional vector space, which we can also think of as being the differentiable manifold that is R3. Okay, so in this case, the manifold is three-dimensional Euclidean space, which is a perfectly differentiable good differentiable manifold, and each object G in SO3 can then be thought of as a rotating action, okay, which rotates some vector in R3 to another vector in R3. So we write, for example, that Gx produces another vector that is x prime, okay? So the domain of this map is the sort of, what do we call this ordinary Cartesian product. The first is the group itself, and then the second set is the differentiable manifold. And the map takes something, in other words, takes a pair in here to give you something in M, okay? In other words, using a particular G, it acts on a particular X to give you Gx, yeah?
But wouldn't that just a group representation of SO3?
That's not a representation. A representation, remember, represents a group by a set of linear operators on vector spaces. So those operators are operators on vector spaces, but M is not necessarily a vector space. It can be in this case, but it's not necessarily a vector space.
But it
So
seems
It's like it. It's like it. No, it doesn't need to have the that homomorphism rule. Okay, that is a crucial thing. The preservation of multiplication, the idea of the homomorphism is important in representation. There's no restriction to this at all.
But this is more general.
This is more general. Yeah, group action is more general. Okay, there's no. I mean, any map will do basically. Now. You see, the group itself is an abstract algebraic thing, right? The set of 3 by 3 special orthogonal matrices. Let's say if you were not a human being, if you were not living in three-dimensional space like us, and if you were something that lives on a two-dimensional space, okay? Let's say if you were an ant. If you were an ant, all you know how to do is to crawl around the surface of a sphere all day long, and you don't know how to jump up and tunnel in and so on and so forth. You live on the surface of a sphere, right? It turns out you can also think of, to this ant, there's a meaningful group action living on this differentiable manifold, which is not R3 now, but the two-dimensional sphere, which is S2, right? The surface of a sphere is S2. It's called S2. That sphere itself is called S2. There is a perfectly good geometrical meaning for the group action where M is S2 instead of R3 also. Okay? Why? Because let's say you take some point that is on the surface of a two-dimensional sphere, and how do you get from one point to another? You can move in a whole bunch of ways. You consider the ant crawling. Infinitely many different ways to get from one point to another, right? But you can also think of any 2 points can be thought of as the endpoints of these two vectors, right? Right? If you imagine that a whole sphere, two-dimensional surface being embedded in a three-dimensional space, then there's a center to that sphere, and then you can think of drawing vectors. But those vectors have to have the same length, right? Because the length is what? Just the radius of the sphere, right? So what's the relationship between these two vectors? You can always think of it as being connected by some rotation, right? You can always think of it as being connected by some rotation. And so therefore, there's another action, so to speak, group action on the manifold, which is S2, which turns out to be a different group action from the same group action of SO3 acting on R3. Okay, so these are just two quite obvious examples, and you can build up many more also. But for our purposes, in terms of talking about the rotation group SO3, these two probably are the most important instances. Okay, the two are very different. For one, the differentiable manifold M is R3. For the other one, the differentiable manifold is S2. R3 and S2 are entirely different manifolds. One is three-dimensional, one is two-dimensional. Okay, but there's a meaningful way to think about something in SO3 taking you between different points in the two spaces. Okay. Now, one very important difference is this. You take any 2 points on the surface of a sphere. There's always some rotation which brings you from this point to this point, right? But supposing I take 2 points here that lie in the same straight line. Is there a rotation which takes me from this point to this point? No. Why? It's not one cannot be a rotated result of the other one because, for one thing, they're of different lengths. Okay? So it's very different as a group action, even though you're talking about the same group. And so there is the possibility of using a particular group in many, many different kinds of group actions. All right? And a mathematical problem, well, depends on what is the manifold of choice. Okay? If the manifold is different, then a group actions becomes a different map altogether, maybe very different also. And we do have to make that distinction. Now, finally, there are many different ways to choose the manifold M. Again, if you were just some ant, okay, in an ant colony, and you were born into this two-dimensional world and you didn't study any geometry, but all of a sudden you didn't study any geometry. All you studied in ant school was the algebra of 3 by 3 special orthogonal matrices, right? So you're given a bunch of things, each one of which is a 3 by 3 special orthogonal matrix. It may not be entirely obvious to you how to study this whole set, which is called SO3, okay? You see what I mean? The algebraic object is quite different. The algebraic object, that is the group SO3, which is abstractly defined as the set of all special orthogonal 3 by 3 matrices, is a distinctly algebraic concept, and it may not be entirely intuitively obvious how to build a particular group action. But in principle, you can always build some group action like this. If you can find a rule which associates something in M to some pair in this product set like this, there has to be a rule. Yeah?
I don't see the difference between SO3 acting on R3 versus S2.
The difference will come in when I introduce this concept of a group action being a transitive action, being a transitive group action. This is one of the things that I'm going to talk about next. Group actions, there are three distinctly different kinds of group actions. First one is called effective group action. The second one is called free group action. And the third one is called transitive group action. A group action is said to be effective if it satisfies a certain condition. A group action is called free if it satisfies some condition. And a group action is called transitive if it satisfies some other condition. There are three different conditions classifying group actions into three different distinct types. These are given in definition 6.5, but since you asked that question, 6.5, 6.6, and 6.7, let's talk about 6.7 first, which is the definition for a transitive group action. Transitive group action is this. Given any 2 points on the manifold M, there's always some group element according to the group action which will take you from one point to another point in M. Now obviously SO3 acting on S2 is transitive, right? Because given any 2 points on a sphere, there's always some rotation which brings you from one point to the other one. But it's not so on R3, which is just the example that I just mentioned. Given these 2 points which lie in the same line in R3, there's no group action, no rotation which will take you from this point to this point, okay? So the same group apply to two different, these are two different actions because the manifold is different, okay? One is transitive, the other one is not, okay? So, all right? You might think that this is splitting hairs, but, but sometimes in proving theorems, these things are important, okay? Now let me go back a little bit first before we come to the definitions of the other two. In physics, the most important situation is when M, the manifold, is a vector space, as in Euclidean R3 space, or Minkowski space-time, as in four-dimensional space-time in special relativity, or in Hilbert spaces in quantum mechanics, okay? All those can be considered as manifolds. Now, there's also another situation where the group action is very important. Consider Lie groups, okay? Now, what are Lie groups? Lie groups are continuous groups so that the set of parameters describing a particular or characterizing a particular element is within a certain continuous range. SO3 is obviously a Lie group because there are three angles specifying a particular rotation, and all those three angles lie in some continuous range of values, okay? So in that sense, I mentioned this already, a Lie group can be considered and in fact is a differentiable manifold. It has, besides a group structure, a topological geometrical structure to it, namely that it is a differentiable manifold. Okay? So you may think, for example, that if we are talking about a Lie group, that this M can be the group itself. Okay? When G is a Lie group. Because when G is a Lie group, it is automatically a differentiable manifold. Okay? So then one of the obvious actions is just multiplication. Right? You can take it's multiplication. You can specify some element in here, G for example, and use that to act on any element in the same G by multiplication. For example, by choosing a particular G, you can build this particular group action, which says that sigma G, I can write it like this, right? Sigma G prime is actually equal to left multiplication of any G prime by some element of your choice, G, okay? So this is called left action because the group multiplication is to the left, okay? The thing that is used to define the particular map, in this case, stands to the left of the thing that you're acting on, although in this case we are sort of explicitly using this kind of notation, a kind of group action, okay? Sometimes you also write the particular map as being G sub sigma sub G for a particular fixed G, and then you can use this to act on any element G prime in the same G to give you GG prime. So this is called left action, and obviously you can define a right action also, okay? This is left action. You can define a right action such that sigma G acts on G prime is equal to G prime G, right? Acting, multiplying on the right. And of course, the two actions are not the same. They're different things. Why? Because group multiplication is not necessarily commutative, okay? Now, this kind of action is actually very useful in the geometrical study of Lie groups, and there's a geometrical side to it that can be used to define, left invariant fields and right invariant fields and so on and so forth. That's very important in the theory of Lie groups, okay? Which maybe if we have time, we're going to talk about later on, okay? You can also write, just to be more specific about this, sometimes you can also write the left action by something like this, where the letter L here stands for left, okay? So left action by some G, acting on any G prime in the same group, is defined to be G multiplying on the left, G prime on the right. And you can define a right action by some G acting on any G prime is equal to G prime G. And obviously the two actions are different, okay? Using a right action acting on some G prime will produce you this. Using the left action acting on the same G prime will produce this, but the two are very different because GG prime is not the same as G prime G in general. Group multiplication is not necessarily commutative, okay? All right, so let's, so that's another important concept which we will come across later. Now finally, let me introduce these other two notions classifying group actions. A group action is said to be effective if the only element that produces the trivial action is the identity itself, okay? In other words, if you have sigma G x, the trivial action is not changing this element at all. This is called a trivial action, okay? If This is true for all x in M. Okay. Let's say there's some group element which always produces the trivial action on anything in M. The condition is this. The whole condition. If this is equal to x for all x in M, then G must necessarily be equal to E. If this statement is true, then the group action is said to be an effective action. In other words, the only group element that produces the trivial action for all elements in M is the identity element. If the group and M and the group action satisfies this condition, then the particular group action is said to be an effective action. Okay? Now, when we come to free is something like this. If every G in G that is not the identity every group element in G that is not the identity has no fixed points. In M. Then the group action is said to be free. Okay. In other words, if you take any non-identity element, okay, it will not have a fixed point. In other words, if you use the non-identity element to act on anything at X, it will produce you something different that is in M. You see the difference between the two, okay? If a group action satisfies the second condition, then the group action is called free, and then I have already mentioned transitive says that if given any pair x1 not equal to x2 in M, there is always a G in G such that let's say gx1 is equal to gx2. There's always some G which takes you from one. Given any pair of points in M, there's always some G that takes you from one point to the other one. If the group action satisfies that, then the group action is said to be transitive. Now, following this description, there's an exercise, a simple exercise, considering these two group actions that I have just mentioned. Okay, both of which. Actually, the problem is stated more generally than SO3. It asks you to consider ON. Actually, not even SON, but ON. Consider the action of ON, the orthogonal group n by n orthogonal matrices acting on the Euclidean space. So the problem asks you to try to figure out whether that particular action, to take in general geometrical meaning of rotation, whether the action is effective, whether the action is free, whether the action is transitive. Okay? So I think it helps if you consider the special case as O3 first, O3 or SO3. Okay? And then you'll see immediately that SO3 acting on R3 is not transitive, but SO3 acting on S2 is transitive, and so on and so forth. Okay? So go home and think about that. That's exercise. Okay, I think I have laid down all the necessary definitions in order to build up the next step. Then comes the next definition, which builds on the definition of group actions. Okay? This is a notion of the little group, or sometimes also called a stabilizer group, corresponding to a particular element X in M, or a particular group action. This notion is very important in representation theory. group theory in general, and I will proceed to present how to apply it for the special case of three-dimensional rotations in just a little bit. But let me first state the general concept first. Actually, there are three names to it. It's called the isotropy group, or called a stabilizer group, sometimes also called a little group. All three terms mean the same thing. Okay, what does an isotropy group mean? So supposing you have a group action, which is a map from G cross M to M, right? Given a particular group action, the isotropy group is some subgroup of the group big G corresponding to a particular element X in M. So say it like this: the isotropy group corresponding to a particular element X in M. So this group, we call it X bracket H bracket X. H is the name of the group. X is the element with respect to which this particular isotropy group is defined, is this, namely that it is all the elements in G such that it does not change X. In other words, X is stabilized. You don't move it, okay? So you don't move it. Now this seems quite abstract, so immediately let me give you an example, okay? Consider the action on S2 of SO3, okay? So let's think of this. SO3 cross S2 to S2, okay? So the group is SO3. The manifold is S2, which is the two-dimensional sphere. And so the group action takes you from some point in general to another point on the same spherical surface. Now, consider some point X on the surface of the sphere. Can you think of a subgroup of SO3 which does not move X at all? Rotation about which axis? Which joins the center to X, right? Quite obvious, right? So if you consider the rotation about this axis by any angle whatsoever, there are infinitely many such rotations, right? In fact, the set of these rotations is isomorphic to which group? SO2. It's rotation on a plane, okay? So in that case, the stabilizer group of this particular point is the set of all rotations about this axis. And it's a subgroup, quite obviously. It's SO2 is a group itself, okay? Set of two-dimensional groups is a group, is an SO group. Well, obviously, there are an infinite number of stabilizer groups because there are an infinite number of points. For each point, there is its own stabilizer group. For each point on the surface, there is its own little group. These three terms mean the same thing, okay? So whenever you talk about an isotropy group, you have to say, with respect to which point in M this particular isotropy group is defined, okay? Now, so this is one example, right? And maybe you can build up some others or so. Can you see right away that considered as a group action, supposing the particular group action is a free action. Supposing a particular group action is a free action, Too bad I just erased that. You have your notes and you can refer to it. Then it's necessarily true that any isotropy group must be just a group of one element, and that element is the identity in the group. Okay? Why is that? It follows directly. And a group action is free if any non-identity element has no trivial action, right? So any non-identity element has to change the point x, okay? So in this case, if the group action is free, there's no non-identity element which change the point. But this thing, in principle, can consist of many, many different rotations. But out of those, there's only one identity. And that is the only one that does not change this, okay? So the group action, if the group action is free, then any little group with respect to any point must be just the trivial group, which just consists of the identity itself. Now, this fact is sometimes useful, okay? And now, let me mention one thing, sort of which is quite obvious, but sometimes people tend to be confused about that. The isotropy group in this case, for the SO3 case and the S2 as the manifold, is isomorphic to SO2, right? The isotropy group corresponding to any point x is isomorphic. Each of these corresponding to different x is isomorphic to SO2. All right? Now, the isotropy group corresponding to any element x is a subset of SO3. It's a subgroup, in fact, because it is in its own right a group. Now, this defines it as a set, but it's also quite obvious that all these things form a group, right? Do you see why? Immediately. Let's say I have two elements in the isotropy group, okay? So that the whole thing is a group, I have to prove a few things according to the definitions of a group. First of all, I have to prove that if these two things are in H, then the product of these two things also are in H. The identity is in H, which is obviously true, okay? Then the multiplication is associative, which is obviously true because group multiplication in any group is always associative. And finally, it has its own inverse and so on and so forth. So we just really need to prove that if there are two H's that are in the same isotropy group, then the product of these two must be in the same isotropy group, and that's quite obvious, okay? So we use the let's see, we use the product of H1, H2, and use it to act on X, okay? This is equal to H1 acting on H2X. But since H2 is in the isotropy group, H2X just yields X, all right? Now then, you further use H1 to act on it, but H1 is also supposed to be in the isotropy group, and so therefore this also produces X. So we have shown that if separately each of H1 and H2 is in the isotropy group, then the product of these two must also be in the isotropy group of the same X because it acts on X to yield back the same X. Okay? So the isotropy, we call this a group because in fact it is a subgroup of the original group G. Okay, so that's quite obvious. So any isotropy group, and there are infinitely many here, okay? Each one is a subgroup of SO3, and each one is isomorphic to SO2. What does that mean? That means there's a one-to-one correspondence between, you know, things in a particular isotropy subgroup to the elements in here, because each one such is a set of two-dimensional rotations, okay? But you have to be clear about one thing. SO2 itself is not a subgroup of SO3. Sometimes you tend to think of it as such, but SO2 is not a subgroup of SO3. Why is that, properly speaking? These are completely different things. Each thing in SO3 must be a what? 3 by 3 matrix. Each thing in SO2 is a 2 by 2 matrix. So two are completely separate sets. So one cannot be a subset of the other one. Okay? But sometimes you can build up isomorphisms between subgroups of one and this other group and so on and so forth. Yeah?
Does it have to do with the fact that this is a manifold that we're working with, so you can zoom in and it looks like a flat plane?
Well, you don't even have to think about the geometrical properties. As I said, you can think of just these in terms of algebraic objects, right? One is a set of 3 by 3 matrices, and the other one is a set of 2 by 2 matrices. So therefore, nothing in the one is something in the other one. So one cannot be a subset of the other.
Right.
But as you said, you can think of these as manifolds. Okay, both SO2 and SO3 are manifolds, and there's a correspondence. Okay, and there's a S manifold. There's an isomorphic structure. Okay. And what exactly is the manifold of SO2? S1, okay? Because SO2 is just characterized by one angle, right? So when theta changes from 0 to 2 pi, that's it. So it's a circle. That's S1, okay? So SO2 is topologically S1, okay? Now topologically, SO3 is something very strange. I think we mentioned that already. You remember what topologically SO3 is? A sphere with antipodal points identified. Something which is very hard to visualize. Okay, something which is quite hard. It's not an ordinary solid sphere. It's not an ordinary solid ball, because an ordinary solid ball has antipodal points being different points, right? But there's this thing which antipodal points are considered to be the same point. Okay. It's like, there's this place that you're living in. Each point in the interior is a separate point. But when you come to the surface, when you are here, all of a sudden, it's the same as being here. Okay? So you live in LA, it's the same as when you're living in some place in China, or something like that. These two are the same. Okay? But as long as you're inside, all the points are different. So SO3 is a very weird thing topologically. SO2 is a very simple thing, which is just S1, okay? And SO4, I don't know. It's hard to imagine what that is, okay? But we do know that, of course, it's a differentiable manifold, and you can prove that according to the definitions of what a differentiable. Any Lie group is a differentiable manifold, okay? Any Lie group is a differentiable manifold. Okay. Now I'm going to introduce yet another concept using the concept of cosets that we have talked about already. Let's look at this thing. Supposing I look at this object. Supposing I look at one such. Oops, going back to this picture. Supposing I look at one such isotropy group. So that isotropy group is a subgroup of SO3. But you can show that it's not an invariant subgroup, okay? It's not an invariant subgroup, and so therefore you cannot really make a quotient group out of it, G divided by some isotropy subgroup. But you can make cosets out of it. Okay? So, even so, I'm going to use the same symbols of quotient. Let's say we talk about a set of left cosets that is obtained by dividing HO3 by some isotropy subgroup Now, I am being a little bit loose in here. This is not a subgroup, but if you consider this as something that's isomorphic to a particular isotropy group, okay, then that isotropy group is a subgroup. But that subgroup, as I said, is not a normal subgroup. So in principle, I cannot make a quotient group out of this, but I can make a set of either left cosets or right cosets out of this, right? Remember that if the subgroup is not a normal subgroup, then you can still bust the group up into different cosets. You can left cosets or right cosets. They're not the same subsets unless the subgroup is a normal subgroup, okay? So if you form this, form this set of cosets, so let's say that this is something that's isomorphic to SO2, and this is some isotropy subgroup, and you can use this to form a set of left cosets, okay? And this is not a normal subgroup, therefore the quotient does not have a group structure. The quotient does not have a group structure, but it does have a manifold structure. It does have a manifold structure. And now, again, we can go back to this, right? Let's say I'm looking at a subgroup, isotropy group corresponding to a particular x in here, hx, okay? That's a subgroup. So I use that subgroup to form the set of left cosets. The form of the set of left cosets can be written in general like this, okay? Where you pick some particular G in SO3, and you multiply through by all the elements in this particular coset, and then you form a set of things, okay? Each one of which is an element in the original group. And as we saw, the left cosets themselves must be disjoint, so they are distinct sets, okay? Any two left cosets cannot intersect in any non-null set element, so therefore all these are disjoint. Now you take these collectively as some set, the set of left cosets. It does not have a group structure unless this is a normal subgroup. So in the case that this is not a normal subgroup, let's say we take the left cosets, you identify each of these things as something in one set. That set does not have a group structure, but it does have a manifold structure. Why? Because it's clearly indicated in this particular example, although this is true in general. You see, now let me see how to develop this. We are going to claim that this is in fact homomorphic to. It does have a manifold structure, and a manifold corresponds to the spherical surface itself. Because of this fact that, let's say if you take any two elements G and G prime in the original group SO3, and supposing G and G prime are in the same isotropy subgroup corresponding to the point X, okay? And we have already seen that G and G prime have the same effect on X, right? Because G acting on, let me see. No, I should say if G and G prime are in the same coset, the same coset generated by a particular isotropy subgroup, then it's clear by definition G prime is equal to G multiplied by H, where H is in the isotropy subgroup. This is the meaning of the left coset. Two things in the same left coset when the two things are related by this manner. Okay? And now, you can show that these two elements, G and G prime, have the same effect on X, right? G and G prime have the same effect on X because G prime acting on X is equal to, since G prime is GH, is equal to GH acting on X. But since H is in the isotropy subgroup, HX is just equal to X. So G prime X is equal to GX. You see that? So the thing is, you take this particular isotropy subgroup, which is HX, you take G and G prime, both of these things, if both of these things are in the same coset, okay, then both of these two things will have the same effect on X as we have just shown. Okay. So so now, supposing I take X to be the identified as the north pole of some sphere, choosing a particular coordinate system. Okay. So if I take this to be the north pole, and the north pole is here, let's say, and so if you want to specify this by polar coordinates, it would be theta is equal to 0, phi is just anything, but whatever. Okay. Or you can use this the rectangular coordinate 0, 0, 1 if this is the z direction. Okay, if this is the north pole, let's say we take X, we take a G, one of those things over there, G. G takes X to something which is GX, which we call Y. Okay. So the idea is this. Any element in here will take X to this same point we have just shown. Okay? Any element will take the north pole to that point. So we can characterize all of these guys in here just by this point. Yeah?
What is that stairs in? Sorry.
What is what?
What is it? What did you label that?
What is the name? The GX is equal to Y, let's say. G takes X to this point, GX, and we simply call that point Y. So let's say G is some element in some coset, left coset in here. I have just shown that any other element in the same coset would have the same effect on this point X. Namely, it takes X to this point Y. So this point Y kind of characterizes everything in here. All right? Supposing I choose another point. Supposing I choose another group element, which is in a different coset. All right? This element will take the point X. This element, that other element, what do you want to call it? G double prime? Okay. This G double prime cannot take X to this one in here. Why? Because if it did, it would be in the same coset. Okay? So that other element, which is sitting in another coset, would take X to some other point, over there, for example. Okay? And similarly, every other element in this coset will take X to this other point. So the idea is that each coset here can be characterized by one particular point on the sphere. So there are as many cosets as there are points on the sphere, so that the set of cosets must then be isomorphic to the set of points on S2. In this sense, we say that this quotient structure in here, the set of cosets is then, it may not have a group structure, but it does have a manifold structure because it's isomorphic to a differentiable manifold. Okay. Now, I'm not going to prove this as a general theorem, but you can actually quote these results. If you have a coset structure as On plus 1 divided by On, pretty much in the same sense that we have over here, okay? Then this has the same manifold structure as Son plus 1 divided by Son. And as generalizable from here, what is this going to be isomorphic to? Sn. That's pretty interesting. The set of cosets is a manifold structure. Okay? And there's another result for UN. So the U's are the unitary elements, okay? So they have more parameters than the O groups. I'm not going to be proving this at all, but you can show also that there's a general relationship like this. It's also isomorphic to some sphere, but this time it's sphere 2n plus 1. That is a bigger sphere because the unitary groups are matrix elements of complex numbers. And each complex number has two real numbers in it. And so the S2n plus 1 is a real sphere, okay, like that. For example, S3, what is S3? S3 is something that's quite common in physics also. It's the subset of points in four-dimensional Euclidean space such that what? So some point in four-dimensional Euclidean space would have four components, right? Like so. I define a subset such that this condition is satisfied. Some constant. Okay? Then the set of points is called S3. If you think, you can think of S3 as being immersed in S4 in pretty much the same way as S1 is immersed in R2. Okay, all the points in R2, but these are the points where x1 squared plus s2 squared is a constant, namely the radius of the sphere. Okay, or you can think of the two-dimensional sphere, spherical surface, as being immersed in R3, but that's the points on this surface must satisfy what condition? That x1 squared plus or x squared plus y squared plus z squared is equal to some constant. In this case, it's the radius of this sphere. So this is S2. Okay. Similarly, you can think of S4, although I cannot draw it now, okay, as being a subset that is immersed in R4. Now, the subset of points must now satisfy this condition in here. Okay. In a similar way, you can think of S anything whatsoever. Okay. You can think of S99. Okay, as being a subspace of R100. And that's a set of points for which the squares of all the 100 coordinates add up to be a constant number, and so on and so forth. Okay? And so definitely you can think of S2n plus 1. So this thing can be any number in number 1. So those are very important topological spaces, both in mathematics and physics. The spheres, these are called as n-spheres. Okay? The n-spheres are very important topological elements. topological spaces in physics. So finally, a term. Things, structures like this is called a homogeneous space. It has a certain manifold structure, and if it's formed out of some quotienting kind of operation like this, it's referred to as a homogeneous space. That just happens to be the term that's used in mathematics. Okay. All right. Let's. I'm going to state and prove a theorem next, but before we do that, let's just rest for a few minutes. Okay, next I'm going to prove a theorem concerning isotropy groups, which will be very useful indeed. So let me discuss things in terms of the group SO3, or draw a picture in terms of group SO3, although this theorem is true in general for any general isotropy group of some group. So you ask the question, the isotropy group in this case corresponds to a particular x, right? And let's say there's some group element, G, which takes you from x to this point, which we call Gx, okay? So corresponding to this element, there's going to be another isotropy group, which is going to be isomorphic to this first isotropy group. But they're different groups, okay? So then the question is, how are those two different groups related to each other? In other words, how is Hgx related to Hx? Obviously, they're not the same thing, okay? And the answer is surprisingly clean, that Hgx is equal to Ghxg inverse, like that. This is a theorem, okay? So that tells you how two different if 2 points are related by some group element G, then this theorem tells you how the isotropy groups corresponding to those two different points are related to each other, okay? So this is theorem 6.1, which is actually stated in very general terms for any group action. Supposing you're given some group action sigma, G, big G being the group and M being the manifold on which it acts, and G in G and X in M, then this is true, okay? Remember, corresponding to each X and M, I can define a particular isotropy subgroup, okay? So here we have two different isotropy subgroups corresponding to two different points in M, and this theorem tells you how the two isotropy groups are related to each other. And the proof is in typical mathematical fashion, when you try to prove two sets are equal to each other, you prove the left is a subset of the right, and then the right is also a subset of X, okay? When you want to prove that this thing is a subset of this thing, you take anything in here, and you prove that thing is also in here, okay? You take any element in here, and then you prove that it's also an element in here, then you will have proved that this is a subset of that. Conversely, you can take anything in here and prove that it's also an element in here. Then you will have proven that this is a subset of this. When A is a subset of B and B is a subset of A, then A must be equal to B as sets. So that's very basic set theory, okay? So, so we start from this side first. So let G prime in HGX. If G prime is in HGX, by definition, G prime acting on GX must be equal to what? GX, right? It doesn't change this thing on which it's acting. Okay? So then, I could write this as, get rid of the bracket sign. So then I have g prime gx is equal to gx. Now let me multiply by g inverse on the left-hand side, okay? So then I have g inverse g prime gx is equal to g inverse gx, but g inverse g is the identity, so therefore this is just equal to x, okay? Oh well, then what do we have? Hence, if you take this thing in here, this thing must be in what? This thing must be in hx, because it doesn't change x, okay? And so therefore, let me define this thing by g double prime, which I define to be g inverse g prime g. Must be in the isotropy group, subgroup corresponding to x. Then g prime, I can write g prime must be equal to what? How can I write g prime in terms of the other things?
G double prime G inverse.
Exactly. G double prime G inverse, right? So simply by multiplying g on the left and g inverse on the right, then I get g prime, okay? What does that tell you? Now the assumption is that, well, the result is that g double prime is in hx. So this is something in hx. Okay? So then I have proven that if g prime is in hgx, then g prime is also inghxg inverse. Okay? A very simple proof. So you have proven that this set is a subset of that set. Okay? So therefore, hgx is a subset of g hx g inverse. Conversely, suppose I have something in here, right? I'm sorry. Let me say g double prime is some g double prime is in here. Let g double prime be in hx. All right. So let g double prime be something in here. Then, by definition, g double prime acting on x must be equal to x. Okay? And so, let me make this thing up. G double prime, G inverse, Gx. That's obtained by multiplying by G on the left-hand side, because this is equal to E. Okay? So must be equal to Gx. Okay? Is that right? You multiply on the left by G on each side. So on the left-hand side, you get G double prime x, because this is E. On the right-hand side, you get Gx. Now, then, if you split up like this, what does that tell you? That tells you where must this be in. This doesn't change Gx, right? So that must be in H of Gx. Okay? So you start off with something in here, then you end up with something in here. So the right-hand side is also a subset of the left-hand side. You see that? reasoning, okay? And so therefore, G H X G inverse is also a subset of HGX. So the subset condition goes in both ways, so therefore the two sets must be equal to each other. Okay? So it's a simple proof of a very neat theorem because it has interesting applications. What is this application? It's called Euler's theorem. Supposedly Euler figured that out a long time ago. Euler, I don't know how much group theory he knew, probably not that much, okay? Obviously he figured this out in some independent way. One of the ways in which it is stated is this. Euler's theorem has to do with how to characterize any particular three-dimensional rotation, okay? Now, if you consider a G, which is in SO3, one of the ways to characterize that particular rotation is by characterizing the direction of the rotational axis, okay? And the angle of rotation about this axis, like so, okay? So altogether there are three angles, right? Theta is one angle, and then you need two angles to characterize a particular direction in three-dimensional space. Because you can reference that direction with respect to some choice of basis, and then these two angles characterizing the direction would be the polar angle and the azimuth angle. I better use a different name for this. Okay. So to characterize a particular rotation, you need three angles. But there's another way to characterize a particular rotation by characterizing a particular rotation as successive, as a succession of three separate rotations, each one about a different axis in space, okay? So let's say that, now let me throw away the names of these angles because it will get confusing, okay? So let's say I take this rotation, and it's a very general rotation, okay? Supposing I call this the first axis, I call this the second axis, I call this the third axis, and R is a particular rotation which is about a certain, the rotation axis is pointed in a certain direction, and the rotation angle is such and such, can always be written as three successive rotations. You read the rotations reading from right to left because this is treated as a left action, so therefore you use this rotation to act upon some vector on the right. So you first rotate about a third axis by some angle psi. You take an object and you rotate it like this, okay? And then you rotate about the second axis. Take the same object. After the first rotation, you take it and rotate about the second axis in a positive sense by some angle theta. This theta is not this theta, so that's why I erased the names of those angles. Now, you would have thought that the third one would be rotating about the first axis, but wrong. You do it with respect to number 3 again, by a different angle, phi. So any rotation can be built up out of a succession of 3 rotations. The first one about the third axis. These are space-fixed axes, okay? The first one about a third axis by a certain angle, the second one about the second axis by a certain angle, and then the third one by about the third axis again by some other angle. These angles, theta, phi, and psi, are called the Euler angles. Theta, phi, and psi are called the Euler angles. Theta, phi, and psi are called the Euler angles. How many of you have seen Euler angles in a classical mechanics course? Some of you haven't taken my classical mechanics. We will, okay? We will be talking about it when we actually talk about when we go to the Hamiltonian formulation dynamics of rigid body rotation. Obviously, when you study the rigid bodies, it is about rotations. A lot of it is about rotations, right? So therefore, we need to have a good way to characterize rotations, and one of the ways to do it is to use this Euler's theorem. So this is the theorem. This is Euler's theorem. Any rotation whatsoever can be built up out of 3 successive rotations. The first one about a third axis, second one about a second axis, and the third one about a third axis also. And so far, these are space-fixed axes. Yeah?
As a curiosity, why don't we care about the third? Why don't we care about R1?
We are going to prove this theorem. It just turns out to be this way. So let me kind of, now, this is a solid object, right? Let's say we have chosen a particular reference frame, 1, 2, 3, like that, okay? So first axis is this way, second axis is this way, third axis is this way. Now, supposing the particular rotation is like this. You take a solid oriented in any way, just put it like this, okay? Supposing my rotational axis is like this, okay? Then physically, that rotation would be this thing going around like that, okay? The whole thing going around like that, okay? This theorem says that, well, you don't have to do that. You can do it first about the third axis by a certain angle, so you go like that. Second axis by a certain angle, then you go like that, okay? Then about the third axis again by yet a different angle, like that. And the result that you build up is necessarily this first rotation, whatever it was. And of course, you have replaced one set of 3 angles, these 3, by another set of angles. But no matter how you do it, you always need 3 angles to specify a particular rotation. Euler's theorem tells you that you can do it like this. What's the advantage of doing like this? Doing it like this enables us to write things in terms of components with respect to the 3 chosen axes, and that's why what we always do in physics, okay? Now, it's somewhat counterintuitive because you might have expected that you do it 1, 2, 3, but it's 3, 2, 3, okay? It just turns out to be that way, and we can use this theorem to prove this. So let's prove this theorem first, and then after we have proved this theorem, then we'll go back to the more conventional way of specifying the Euler angles, okay? Which instructs you to rotate things in terms of moving frames rather than fixed frames. Let's see, so how do we prove this? So we consider some arbitrary rotation R, and we look at its action on, let's say, some point that is the North Pole. And we're going to write using a particular set of axes. That, let's say this North Pole x is the point 0, 0, 1, right? Consider the unit sphere, okay? So some point on the North Pole that we call 0, 0, 1. And so this is the point x, which is the North Pole. And let's say this particular, whatever it is, the r takes x to y. The r takes x to y. This rotation rotates x to y, like that. And so we write Rx is equal to y. And y is some general point, and so we characterize this general point by its polar angle. So y is the point theta phi, let's say, okay, some polar angle phi like that, okay. So let's say y is some point theta phi, and r takes x to y. Actually, let me draw a better figure, the one that is in the book. Say that this is the North Pole right here, and these are the three axes. And so that's the point X. And let's say Y. Y is over here, and so I'm going to draw a latitude circle crossing Y. And this Y here this Y is characterized by the two polar angles theta and phi. You remember this setup? That's how you define the polar angles of a certain point on the sphere. Okay? All right, and so now if you look at this point Y in here, you can go there by a route which goes like this. You first rotate around the second axis, okay, by the angle theta. You first rotate around the second, which is this one, E2 in here. This is E3. If you first rotate around this axis, then you would end up, draw this longitude circle, then you would end up here, right? By an angle theta, then you would end up there. Okay? You take this point at the North Pole, rotate it about this axis, this point goes around this circle in here, and let's say you want a point which is the intersection of this circle and this latitude circle on which Y lies. Okay? So this is the rotation. On going from here to here, it's carried out by the rotation about the second axis by an angle theta. Okay? Now, how then would you go to Y? You move along the latitude circle, right? Which means moving along the latitude circle, which means rotating about the third axis. By how much? Precisely by the angle phi. Okay? Oh, by the way, this longitude circle is the one corresponding to phi is equal to 0, let's say. Okay? And so then you do R3 phi. And so take successively these two acting on X, you're going to get to Y, which is at the same time R acting on X. Now these two are different rotations, okay? But they take you, they both of them take you from X to Y. Okay? They both go from X to Y. By definition, R goes from X to Y, and I have constructed explicitly this other rotation which also takes you from X to Y, the same two endpoints. Okay? And I'm going to write this one as G. I'm going to write this one as G. Now G, being a product of two rotations, must be another rotation. Okay, it's G and SO3. Okay? So G, by definition, equal to R3 phi R2 theta must be something in SO3. Okay, now the rotation, I can, whatever this is, okay, let's say I consider these two elements, R and G, okay, I can always introduce some other SO3 element, G prime, such that R is equal to G prime G, always, right? Because apparently I can just choose G prime to be equal to what? R to be R times G inverse, right? Given any R in G, G prime being defined to be RG inverse must be equal to R. Okay, G prime times G must be equal to R. Then G prime acting on Gx must be what? Must be equal to RG inverse acting on Gx, because G prime is defined to be that. That must be equal to Rx. But Rx is Y. Okay? Rx is Y. And Y is also equal to Gx. Okay? Right? And so therefore G prime must lie in the isotropy subgroup of Gx. Okay? So therefore G prime must lie in the isotropy subgroup of Gx, but Gx is equal to Rx, so I'm going to write HRX also. Okay? Now, because of the theorem that we have just written, use this theorem in here, G prime lying in here must be expressible as something like this, which must be equal to G times something in the isotropy group of X, but since X is the north pole, the isotropy group must be the rotation about the third axis. So it's some rotation about the third axis. Okay? So because of this, I can now write G prime, because of this theorem also, must be equal to G prime, must be equal to G multiplied by R3. Now I don't know which rotation, so let me just leave this angle to be arbitrary. That is some rotation about R3. Okay? So this follows from this, right? So here's where we make active use of this result in here. And now, and so R is equal to G prime G. So R now must be equal to G prime G. G prime is equal to G R3 psi G minus 1, that's G prime, and then multiplied by G. And that is equal to G times what? These two multiplies to be the identity, so that must be equal to G times R3 psi. Okay? So what was G? G was that. Okay, so any R is now expressible as G multiplied by R3, and G was proven to be R3 phi, R2 theta, R3 psi. So we have proved this theorem. Okay? Now, without this, it would be, I don't know if you want to try it, would be kind of hard to prove. I don't know how Euler did that. Obviously, he was thinking at light speed, so it's different. Thinking in a hypersphere, so it's different. He did not have to use group theory. Okay. What do we do with this? Now, the idea is this. So we have proven this, theorem in here, but some of you who have taken classical mechanics will realize that this is exactly the same thing as doing something different. You take these three angles, which goes in this order, psi, theta, phi, but I can take three rotations in the opposite order, starting with this one first, and then with this one, and finally with this one, and it will achieve the same result. And so you start off with something like this, right? So, and this is, I'll draw this, and then next time we come back, we'll prove this. So let's say you start off with epsilon 1, epsilon 2. This is like the unrotated state. So, oh, I should do this in the opposite order. You take phi first, you always write this one first, and then you take theta, and then you take psi. Which one is this? This one is rotating with respect to the third axis by the angle phi. So you rotate this, by the angle phi. And so I'm going to draw a circle like that, okay? So you end up with a new system, right? Now let's think of, rotating the frame in here, right? So the new frame will be, let me just dot line the original frame, like so, okay? So the new frames, this is going to be some intermediate one, which I'm going to call, I call them E, I guess. Epsilon E doesn't matter, epsilon E doesn't matter. E1, E2, E3. So this one I call E1 prime. After the first rotation, this is E2 prime like that. Okay? So the first one is rotating by the original third axis by the angle phi. And then the next one is now to rotate about the new E2, the new 2 axis, which is this one. Okay? So whereas in this equation, all these are the original directions of the original frame. All this is you build on successive new frames in here. This is a different way of doing this, okay? So you now rotate about the new second axis by some angle theta, which means this axis is not changed, but then these two will kind of move along this circle, so that this one will become this one, okay? And this one will become this one, okay? And by this angle theta in here, so that it's like this. So now let me dot the, dot line the ones that have been changed. Is that okay? So that's after the second step. So that's after the second step. So now this becomes the E3 prime. This is the E3 prime. I call it E3 prime, and I call this E1. I have an E1 prime, so this one, let me call E1 double prime, okay? I now finally rotate about the third axis, which is this one. This is a new third one. So rotate about the third axis again by this angle phi. And so your new one will look like, what does it look like? So now about rotating about this one, so the new axis, whoops. In the second rotation, this remains unchanged, right? So 1, 2 planes, the second one like that. Now you rotate about this one, so this goes, the new final axis would be like that. You rotate by this angle, by psi like that. So, so this is the final new axis, okay, which is I'm going to draw by the double lines, the final axis. So when you have rotated by these 3 successive steps, and remember by this way of doing this, each step is built upon the rotated frame already, okay? You will have achieved exactly the same result as this. This is the more usual way to describe the same 3 Euler angles in classical mechanics textbooks and also in quantum mechanics textbooks when you consider representations of a rotation group. And you can also go from this to this by using the isotropy subgroup theorem like that. We're going to come back and prove that next time, okay? So the isotropy subgroup has a very, very interesting is a very interesting concept, which in the form of this theorem in here provides us with a very neat and relatively easy proof of a very important result, both in classical mechanics and in quantum mechanics. That is called Euler's theorem, which gives you a particular way to describe rotations using three Euler angles, phi, theta, and psi. Any rotation can be built up in this, either in this way or in this way. Okay. All right. Let's stop here and.